Good morning, everyone. So today our meeting is with Professor Terry Mart. Please welcome Professor Terry Mart.
Thank you very much, Fitri. Good morning, very good morning, ladies and gentlemen. I call you gentlemen and ladies. Yeah. Today I will talk about a little bit about my research, but before that, I would like to introduce myself. This is my name, and you can find it in the physics UI homepage. And if you want to know me more, you can find it there. So I started to become the staff in this department in the year of 1990, 23 years ago, and 12 years ago, I became professor in this department. And as you can see that my research is mostly about on photo production. On electro production is also almost similar because here we use real photon and here we use electron instead of photon. And I'm also interested in electromagnetic and hadronic compactors. Today I will talk about electromagnetic compactors only, and electromagnetic compactor of proton is very specific. And my research is also in the region or in the topics of photo and electroproduction of hypernuclei. So you know the nucleus, the nuclear in the nuclear physics, we know that nucleus is, for example, neutron, helium, lithium, and so on, uranium, plutonium, etc. But beyond that, we have also nuclei. Hypernucleus. Hypernucleus is very interesting because we eliminate one of the proton or neutron inside this nucleus and we replace it with the lambda hyperon. So it is called hypernucleus. You know that because of this process, the energy levels of this nucleus is very different from the conventional nucleus. So people are interested in because we know that in the nuclear reactors or even in the nuclear bombs, you know Oppenheimer is very well known right now. Yeah, the film, the movies. It harnesses the energy levels of the nucleus. So this is very interesting. And we have also investigated the hadronic structures. I will talk about this later or maybe beyond this, outside this lecture because we have very limited time. And you know that we can also, as a nuclear physicist, we can also move to neutron star because in the star, there is only in the quotation mark, only nuclear reaction occur. So in principle, there is no chemical reaction, nuclear reaction. And if we go to the neutron star or if we investigate the neutron star, it is much simpler because neutron star in principle contain only neutron. I will talk about this later if you are interested in because our topic today is electromagnetic. And I have also model which I put in the internet, but this is not in this university because it was put in 2000, in the year of 2000, because 23 years ago the internet here was not so stable, so I put it in Mainz where I I received my PhD in 1996. So it's more than 20 years ago, yeah. We put it there, and this model was used or has been used 1,000 times by experimentalists and theorists. For experimentalists, they would like to predict how much the probability of this reaction, because it is important, because experimentalists should submit a proposal to request for beam time. You know beam time? If we have accelerator which accelerate electron, for example, electrons, and it's quite costly. Yeah. It's very expensive, because to accelerate electron we need megawatt electricity. We need human resources to watch or to control everything in order. So it's very expensive. So experimentalists, before they do experiment, they should request for beam time, and this beam time is also long, because the probability of this reaction to occur is very small. So sometimes experimentalists ask for 1 week beam time continuously, or without stop, or even 1 month. For very rare experiment, or very let's say small probability experiment, they need months of the beam time. So it is very expensive. So they have to request for beam time. They should make proposal. There is a PAC is a program advisory committee which evaluate the proposal, and they give only the beam time for a very important purpose. So the experimenters should compete to obtain this beam time, and they have to make a good proposal, and they have to have very strong theoretical support. So usually for Keon production, they consult this homepage, because this is easy, gratis. You don't have free of charge. You don't have to pay, because just click. Yeah. And for theories, they also need this model just to compare the prediction of this model to their theory. So this is my research. But if you go to my publication here, nowadays I also working in several fields, just because I have to become a supervisor of several PhD students here, which is beyond particle physics. For example, in geophysics, I have 1 student. In medical physics, I have several students. 2 of them have already got PhD, yeah, and become staff here. So as you can see, maybe I'm also working in medical physics, geophysics, etc., and even education physics. Yeah. Okay, now let's go back to our business. Do you have questions about this? No? Just raise the hand, yeah, because I would like that this lecture is not so formal, because this is not well, this is not formal lecture actually. Yeah. Let me start. How to start? You, yeah, you full screen. Yeah. You. Yeah. Yeah. Thank you very much. So let me start the lecture today. In the beginning, I would like to present my main research, namely the Keon photo production and electroproduction. But to this end, we need some background in relativistic quantum mechanics. And I think it is almost impossible to introduce you quantum relativistic quantum mechanics in 1 hour, or even in 30 minutes. So I decided just to talk about the proton radius problem because proton is very well known in particle and nuclear physics. Yeah. Well, okay, just for breaking ice. Yeah. What do you know about proton? I would like to hear from some of you. Yeah, please raise your hand if you know proton. What is proton? Three, yeah, just you don't have to be afraid of me. Yeah? I'm not your professor. What about, oh, yeah, what? Excuse me? Positive charge. Yeah, it has a positive charge plus E. If E is equal 1.6 times 10 to the minus 19. Yeah, hold on. Very good. Yeah, please. Who else? What is proton? What do you know about proton? Hmm? Fermion. Very good. Fermion has spin 1 half. It has spin 1 half. This fermion. Well, what is proton or what do you know about protons? Yeah, you smile. Maybe you think about proton. Proton is my friend. Every day I talk about proton. Every day I'm dreaming of proton. Yeah, once again, what do you know about protons before I talk about the proton radius problem? Who found proton or who observed proton for the first time? Hmm? Rutherford. Rutherford. Well, maybe yes, you are right. On more than 100 years ago, Ernest Rutherford. We have Rutherford cross-section. What else? What do you know about proton? This it is left with one very important. Located in nucleus. This is almost what I want to hear. Almost located in the nucleus. Okay, because I have very limited time also. Yeah. Let me tell you that the important thing is constituent of the nucleus. Inside the nucleus, we have proton and neutrons. Yeah. Okay, so in principle, this is the contents of my lecture today. I would like to talk about what is proton, how proton is built from quarks. You have heard about quarks. How can we investigate proton and the problems, and also I also put some of my last progress in the research of protons. We have submitted together with one of my graduate students, submitted to a journal, but it is still under review. Yeah, let's go to this. What is proton? It is found more than 100 years ago by Ernest Rutherford. It is a constituent of the atomic nucleus. The simplest nucleus is neutron. Of course, you can say, sir, the simplest nucleus is proton because hydrogen, yeah, hydrogen atom has the proton, the nucleus. But what the nucleus I mean here is the nucleus which has strong interaction inside the nucleus. So you can imagine that this is the deuterium, which consists of neutron in the nucleus in the core of this atom, and the neutron consists of one neutron and one proton. Okay. Now, you know, of course, that the neutron has neutron charge or has no charge. Yeah. Is that right? Yeah. Yeah, I know. Why? Because if we could go inside or into the neutron, we see the charge distribution inside it. But the net charge outside this neutron is zero or neutral. But inside the neutron, there is a charge distribution. That means it is not chargeless at all. Why? Because the proton and neutron are built from quarks. So there are 6 type of quarks, but I would like to present or tell you only 2 of them, namely the simplest ones, namely the quark up and quark down. So why people can say that proton consists of 3 quarks? Because this is the easiest thing, yeah. Of course, there are a lot of calculation behind this. The quark up has charge plus 2/3, 2 divided by 3. In the units of plus E, E is equal 1.6 times 19 coulomb. So if you have 2 quarks, 2 up quarks, and you have 1 down quark, you sum up it, the charge is plus 1. In the neutron case, we have 2 down quarks and 1 up quark. 2 down quarks, this is minus 1/3, this is minus 1/3, and this is plus 2/3. Sum 0. But inside the neutron, these quarks are moving in chaotic manner. So the movement of these 3 quarks creates the charge distribution inside the neutron. Of course, outside the neutron, you can feel the charge is 0. You can feel, I mean, you can measure. Okay. Now this is the basic principle of this quark. Of course, there are a lot of, and not only a lot of, very complicated calculation behind. The spin is also matched in this case because the spin of the quark is 1/2. So if you combine this summation, this must be performed in the factor basis. So if you perform the addition of this 3 spin, you can have 1/2 spin. Could you have also a 3/2 spin? Yes, you could, but there is no proton with spin 3/2. We can so-called excite the proton to the spin 3/2, but we need energy to do that. This is also my business. We call it nucleon resonance. Nucleon resonances. But this is beyond the topic of our lecture today, because otherwise you have to maybe to study with me for 2 or 3 years of this topic. Okay. So how do we do that? Take 1/2 up, take 1/2 up, and minus 1/2 for down, for example, and you sum it up, you have 1/2 spin. There are a lot of story about this quark. For example, if you calculate seriously, you will finally know that this model violates the Pauli principle. Why Pauli principle? Because in the case of nucleon resonances, we have so-called delta resonances, which has spin 3/2, which has we call it charm numbers there. Oh no. not jump. Sorry, I mistake. What do you call it? Phase. People call this like phase up, down. Okay, I will tell you if I immediately know that. Yeah. So for delta, we have 3 up square because the chart is plus 2e. So we have 2 up square, which spin up. Yeah. And then finally, if you do a very comprehensive calculation, you will end up with the non-antisymmetric wave function. Pauli states that fermions should have antisymmetric wave function. So then people add in this quark theory the color quantum number. So the color is, for example, red, green, blue. It works like this up, down, and you can finally have the antisymmetric wave function of the protons. Yeah, proton is fermions. Otherwise, Mr. Pauli would be very angry. Yeah. Okay. So far, is there any question? No. I will go to some formulation, mathematical formula. For that, actually, you need the relativistic quantum mechanics basic, but I would like to consider this like Stephen Weinberg. Do you know Stephen Weinberg? This is a very well-known physicist. He has passed away, yeah, this year or last year maybe. He wrote a book, very good books, with the title of The First 3 Minutes. Have you ever heard about it? Maybe you have heard about the brief history of time from Stephen Hawking. Yeah, maybe one of you. It's very good book also, but more popular than Stephen Weinberg. Weinberg's book is much better from my point of view or from my thinking, because Weinberg says, well, I give the formula, but I consider the reader of this book is like a very smart lawyer or attorney who would like to see the proof. But of course, the attorney or the lawyer shouldn't have to process the proof just to see the proof. So just sit back and relax to see this formula. Don't be afraid. Yeah. Now, let me tell you the experiment. How can we see the problem? See the quotation mark. We know that the magnification of the microscope is limited by the wavelength used. So, for example, for the visible light, visible microscope using the visible wavelength, we are limited to maybe about 5,500 nanometer or 5,000, something like that. Beyond that or below that, we can see the object. The size of the proton is of the order of femtometer. Femtometer means 10 to the minus 15 meter. Yeah, 10 to the 15. Let's compare with visible light. It is approximately, if I'm not mistaken, 500 nanometer or 5,000 angstrom. 1,000 angstrom, that means about 10 to the minus 7. Because we cannot see it. We cannot see proton by using the visible light. Using X-ray, X-ray diffraction, we can see the crystal, the spacing between crystal. The spacing is about 1 angstrom, the distance. 10 to the minus 10 meters. Still too big or too large compared to the size of proton. Now, go to the electron microscope. Why we cannot see the proton using electron microscope? The largest, for example, accelerator inside the electron microscope using 1000 keV voltage. This is very, very high voltage. Yeah, 10,000 volt. So you have to accelerate the electron using 10,000 volt. The wavelength is about 10 to the minus 12. Still too large to see the proton. So we cannot see the proton using electron microscope, but we can use the principle of electron microscope to see the protons, namely by using the accelerator, electron-proton scattering. I will talk about this later. We can use gamma ray because gamma ray is, this is no longer we call it light, it is ray. It can have very small wavelength. It depends on the energy of this gamma ray. We can also use the virtual gamma ray, namely the gamma ray, which is created by the interaction between electron and proton. You know that I can have real gamma, that means real photons, if I use Bremsstrahlung. You know Bremsstrahlung? If I accelerate electron and hit it to, for example, diamond, the electron will be decelerated quickly, and as a consequence of the energy conservation, it emits gamma. Real photon. This is the real photon. But if we interact electron directly with proton, theoretically we, let's say, we make this electron, we push this electron to emit a gamma ray, but this is virtual gamma, theoretically. Yeah. So let's see this. Yeah, just sit back and relax. This is a not very horrible equation, but here in this department, I give a lecture about relativistic quantum mechanics. But to enter this relativistic quantum mechanics, you have the prerequisite is quantum mechanics 1 and quantum mechanics 2. Yeah, so 3 semester of quantum mechanics. Yeah, and then you come to this equation. Yeah, but today just sit back and relax, just enjoy this equation like when you see the picture of Mona Lisa, you like it, yeah, or Doraemon, something like that. Nowadays, anime. The last film of anime, story about one girl, Suzume. I know that because my daughter would like to watch this movie, so I went to the movie with her. Yeah? But unfortunately, my 2 daughters have watched the Barbie, so I just watched Oppenheimer because it is easier to watch Oppenheimer rather than Barbie. Yeah? Okay, let me go to this electron-proton scattering. So here is the picture. The picture how we scatter electron and proton. Here is the electron and here is the proton. So this is needed for the YouTube. Yeah, like not have to put like this maybe. Yeah. So this electron come here and scattered. This is proton. In the lab system, proton is not moving. Proton is at rest, electron is coming, and it is empty. But in the CF, center of momentum, I would like to say momentum of mass, because we will talk about photon, which does not have mass, but has momentum. In the center of momentum, we can say like this. The movement, the proton is moving to the left of me, the electron to the right. It interacts. It emits virtual photon. So we have the so-called, we have a tool which is called payment diagram. Payment diagram. Mr. Payment found this diagram and he put the payment rules to calculate the probability of this reaction. So this is the electron going to closer to the proton. The proton is also going to closer to the electron. And after they interact, they scatter. Electron goes there, proton here. The interaction, the physicists believe, this is not the same as the religious belief, yeah? Physicists believe that there is no what they call it, what they call the mystic case interaction without anything. Yeah. Physicists believe that the interaction must be brought or must be done by something, by exchanging particle. Physicists believe that. Now the particle in this case is a photon, virtual photon. Why? In relativistic quantum mechanics, you can calculate the mass of the particle by squaring of this 4 momentum. Why 4 momentum, not 3 momentum? Because we are working in relativistic quantum mechanics. Mr. Einstein said that the time belongs to the 4th dimension. Yeah? So we have 4 position and we have 4 momentum. If you square this 4 momentum, if the particle is outside, mean that free, then you have the mass square. But in this case, if you square this momentum of this virtual photon, you have minus quantity. So it is not real to say that, or it is impossible to say that the mass is negative. But okay, if you have theory, sometimes people say, okay, the mass is imaginary. It is beyond the negative. Yeah? The mass is always positive in our convention. So this is the virtual photon. And Mr. Payment has put the rule, if you have this vertex, so-called vertex, you have this these quantities, yeah. I is square root of -1, E is the charge of proton, charge of electron, if you put minus here, and gamma mu is a Dirac matrix. If you put mu there, means that this is 4 quantities in 4 dimensions. And we have this is minus I, this is G, G is so-called matrix, and here is the interaction with the protons. You have this term. This is funny term because you have F1 and F2 here. Why is this not like I times E times gamma mu? Because proton has so-called structure. Electron up to now is considered as a point particle, but proton is not. Proton has structure because physicists believe proton is constructed or is built from 3 quarks. So if you have 3 quarks inside, then you have structure. If you build this building, yeah, of course, then it has structure because it is not elementary particle. But 1 electron is structureless because it does not contain any quark inside. Electron is elementary particle, so it's very simple term in the interaction with the virtual photon. But proton has structure; it has F1 and F2, which are called the Fermi and Dirac compact. Dirac and Pauli, sorry, Dirac and Pauli. Dirac and Pauli compact. Here is it, 1 and. So what we are what we are doing in this theoretical lab, usually we collect these terms and then we obtain the so-called scattering amplitude. So just collect it. This is from the from this electron. This is from the virtual photon. You see that this is mu divided by q square, and this is yeah, don't like this. Okay, this is coming from the Prof term. Yeah. Now, in the relativistic quantum mechanics, we have to obtain the cross section. Why? Because the cross section can be measured by experimental. So cross section acts or can be considered as something like communication tools between theorists and experimentalists. Theorists predict the cross-section, experimentalists measure the cross-section. So they can meet together in the cross-section. Cross-section is one of the observables. Observables means something that can be observed. Cause observed can be observed here in quotation mark because it depends on the technology to observe that. So we have to, because the initial electron and the initial proton, also the final electron and the final proton, their spins are not observed, we have to statistically average the spins in order to get the spin effect statistically correct. So this is done, or this is performed through this equation. And finally, we have the lepton tensor, L, the electron tensor, L mu term. Remember that K prime belongs to the final electron, K belongs to the initial electron, and Q square, Q is the difference between K and K prime. Yeah, yeah. And this is the hadronic tensor, which actually belongs to the proton. This belongs to the electron. This belongs to the proton. We have here the formula which involves F1 and F2. Now, this is not the cross-section. The cross-section itself okay, maybe now I have to, oh yeah. So after some algebras, I put here some algebras in the books, after a little of algebra. Yeah. Sometimes they are very, very, very proud to say that after a little calculation, of course, 2 pages in the quantum mechanics book, we have this formula for this cross-section. This is the cross-section of the electron-proton scattering measured in the lab system, lab system, .cm. And this is the cross-section between two fermions if the fermions do not have structure. No structure, NS. Yeah, no structure. This is the cross-section if the scattering involves no structure, and this is the measured or the real cross-section. So the real cross-section is the cross-section of the non-structured particles, which can be calculated theoretically times this. We have actually simplify the F1 and F2 using this so-called electric and magnetic compact. So we replace the Dirac and Pauli compactors with this GE and GM, which are electric and magnetic. This is the combination. Why? Because it's easier. If we have this formula, this formula looks like this: A plus B tangent square. So you can do the so-called least square fit in order to obtain A and B if you measure this as a function of theta. Yeah. Okay, this is standard of calculation in the basic experimental physics, yeah, which maybe you have done in the first year. You have measured this as a function of tangent square theta, and you can, if you have data, you can obtain A and B. Once you have A and B, you have GE and GM. Yeah. This is called the Rosenbluth separation method. Rosenbluth found. Now, this is the result. This is the result of the GE, electric compact. Electric compactors, this is all data, yeah, can be fitted nicely, very good, with very simple so-called dipole compactor. The formula is very, very simple. And people was very impressed or astonished by this 0.71. Is there something special with this 0.71? Because it fits the data, all data. And after searching hundreds of references, I found there is nothing special about 0.75, 71. Why? Because using this compactor, you cannot explain the new data. You could explain the old data. This is the old data. Using this formula, very simple formula. Yeah, this is the result of the of our calculation. If we make a least square fit of this cross section as function of theta, we obtain A and B. If we obtain A and B, that means this factor and this factor, we can obtain GE and GM. I present here only GE, the electric compactor of the proton, as a function of Q square. Q square is so-called momentum transfer. Momentum transfer, the difference between K prime. Yeah. Okay. Now, what people said, what the hell of this compactor? Yeah. Why this is important? Why you are you spend 20 or 30 years, yeah, studying this compactor? What is the importance? In the non-relativistic regime, I'm saying non-relativistic because in relativistically this is somewhat wrong, but in the non-relativistic, in the nuclear physics, this is true. The compactor is nothing but Fourier transform of the charge distribution inside the proton. So in the beginning of this lecture, I talked about the charge distribution inside the neutron and also proton, which are created by the movement of the quarks inside the neutron and proton. So if you write the charge distribution inside the proton as, or in terms of rho function x, then once you so-called Fourier transform it, you will have the compact. This is the expansion of exponential IQ dot x. Yeah, this is the expansion of this exponent. Yeah, this is really Fourier transform. Now, if I stop at second term, the first term of course becomes 1 because rho is normalized to 1 in the integration of rho, yeah, over B volume will result in 1, but the second term looks like this. This IQ dot x will produce this term. And the rest, I call the terms with the order of Q port and larger. Okay, this is the average of R square. The definition is like this. This is nothing but this volume integration. Yeah, this is R square. And as a consequence, if I differentiate this to Q square, yeah, differentiate this to Q square, this will become 1. This will have Q square terms. Yeah, this is 0. If I differentiate to Q square, this will be 0. This will be minus 1/6 times R square average. And this is the rest is a term which contains Q square, Q port, which you can kill by putting Q square equals 0. Okay. If you put or if you calculate this differentiation at Q square equals 0, you will have only this term which survive. Other terms do not survive because it contains Q square. You put Q square equals 0, this is killed. Because it is 0, and you can. Then, if you put minus 1/6 here, you will have this formula. This is R square average equals to minus 6 times differentiation or derivative compactor at Q square. By using this formula, people estimate or calculate the radius of the point, which will become now very, very hot in the experiment, in the research. So this is very simple formula. The radius, of course, is taken. Sorry, this is not minus 1. This is plus. Yeah, plus the square root. I will correct this. R is the square root. Okay, do you have question of this formula? How can we measure or how can we calculate the proton radius? Yeah, using this equation. So once you have the compactor of a particle, you can estimate the radius. This is called the root mean square. Root mean square radius, because you have to root this. And this is square. This is average. Root mean square. Mean is average. Okay. Now, if you do not have question, I will move to the proton radius problem or proton radius puzzle. This is I would say this is funny because it was became hot topics in the research when it was published in Nature a long time ago. Yeah, Nature in 2010. No, yeah, 2010. This group measured the radius of the proton not using electron proton scan. They use the muonic hydrogen. Well, to show the formula of this muonic hydrogen atom, why it can produce radius, electrical radius of the proton, of course, you need one more lecture. This lecture only concerned about electron-proton scattering, which can produce the, or through which we can estimate the radius. Yeah, they published it in Nature in 2010. The value of the radius is 0.84. Let's say stop it. 84 femtometer or Fermi. Yeah. Now, at that time, the believed radius, which was a standard radius, was approximately 0.88. Okay? If you consider this 6, then we have 0.88. So the difference is only 0.04 component. And they say this is proton radius puzzle. I said, well, this is funny, but people think very much because in the muonic hydrogen atom, they use only quantum electrodynamics, QED. They do not use quantum hydrodynamics. Yeah, quantum hydrodynamics or QCD, quantum thermodynamics. QED was considered very precise because it involved only electromagnetic interaction, which is very weak. So the so-called perturbative calculation is precise, very precise. Why? Do you know perturbative calculation? If you expand, if you expand, for example, A minus X, let me like this. So if I have e power of X, we can expand this like this, 1 plus X squared, etc. Okay? Yeah. Consider X equal to, for example, 0.001. Of course, I can produce this number quickly, approximately, and this is precise. Okay? But if you consider X equal to, let's say, 2, now you have to consider every term because this is not small. Yeah? This is not small. The third term is very small because this is 10 to the minus 6, yeah, divided by 2. Very small. So this is the something like you can imagine. This is quantum electrodynamics where the interaction is very weak. You can stop at the second order, but this is the hadronic interaction, strong interaction, which is QCD, quantum thermodynamics, where you have to calculate everything. Now, well, in the electron proton scattering, of course, we still calculate or use QED, quantum electrodynamics, but proton has strong interaction. So people are afraid that the proton is not precisely calculated if you do not use quantum thermodynamics. But quantum electrodynamics is used for this calculation. It does not need quantum thermodynamics, so people consider this is very precise, and people ask why. Almost 100 years we believe this number. This is proton radius value. And then people in mind repeat the experiment using very precise electron, very precise proton, very precise, precise here to measure the electron and proton kinematics, and also very precise detectors. They found the same, not this. Most of the electron-proton scattering experiment produce this number. But why the muonic hydrogen atom experiment obtain very different? So this is the puzzle. Then people ask which one is wrong, and maybe there are about 1,000 papers concerning about this from the quantum electrodynamics, the simplest calculation, until extra dimension. People say that this electron enters the extra dimension, maybe. Yeah. which you are not able to calculate. Okay, but people consider different calculation using this electron proton scattering. They found some of the calculation found very good agreement with the ionic hydrogen atom, but some of them has different result. Now in 2000, I think in 2013, exactly 10 years ago, I and my colleague here speculate. 10 years ago, I was still young. So young people are allowed to speculate. Nowadays, I'm old. I have to be careful and speculate. What kind of speculation we made? We speculate that we assume that proton radii are not identical. One proton to other protons have different radii. Okay, that's our assumption. Well, physicists can assume everything, yeah, as long as you have a very good probe, evidence, then it's okay. And then, if we assume the proton radii are identical, what experimentally measured is the radii is distributed in certain range. What experimental is measured is the average. That's our assumption. Average. Let's say the middle value is R1. And then this R1, the variation of this R can be related to the solution of the lambda. Lambda is the cutoff inside the proton compound. Well, what is lambda? Let me go back here. I will talk about lambda later. In general, this is lambda. If I put this lambda square, then I have general dipole compound. This lambda, we can vary and we can calculate the average. So physically, we said that proton may deform. This is taken from this paper, physical review C, 2006. The proton can have a form of spherical, also this is prolate, yeah, this is prolate. Correct. And even if you can also have oblate. Proton may deform, then the definition of radius cost gets blurred. Yeah. How can you define the radius of the proton if the proton has this form? So our assumption is that when experimentalists measure the protons, measure the electron proton scattering, the protons have different radii. Okay, this is also another let's say calculation which support the assumption that the proton radius are not unique. So this is very simple calculation which we made 10 years ago. This is the cross section which I showed you before, but I use this scaling to eliminate GM. Previously, we have GM here, GE and GM. Using this scaling, we have only GE. Now, we have to average this cross-section. If we average this cross-section, that means we average the form factors. This is stable. This is constant. And then we assume that for decades, people believe that the average of this form factor is this one. This is called standard dipole, which I told you in the beginning. People are very impressed with 0.71. Is there something behind this number? Yeah. So for decades, people believe this. Now, using dipole form factors, general dipole form factor, we have this, yeah. We have to average this. Then what we have, this one. We have, from this calculation, we have the radius of the proton closer to the result of the muonic hydrogen atom. Muonic hydrogen atom is 0.84. We have 0.3. We have also magnetic radius, but I will not talk about that today. And this is the comparison of our work. So this is the muonic hydrogen atom is here, 0.84 Fermi or femtometric. This is the result of our calculation, and this is the result of dispersion relation, and this is the core data. This is the what people believe for decades or for this 100 years, and the green one is the very precise electron proton scattering experiment. So we have still discrepancy. We still have the problem. That means the problem is not solved. Well, this is 10 years ago, yeah. 3 months after we published this paper, we have been criticized that our calculation is wrong. Well, okay. I was very happy because when there is comment, I can reply to comment. I have one more paper, something like that. Young people like to have more papers, yeah. But very, very surprisingly, 3 years after that, I was criticized by very senior physicist who spent his lifetime for investigating the problem. So I respect him very much, yeah, because he spent the whole of his life for proton. So he must be very expert. He said that my calculation was wrong. Well, I was still young 10 years ago. I said that my calculation is right. So we fight each other, yeah. The editor of Physical Review asked the senior consultant editor to solve our differences. What the senior consulting editor of Physical Review said, he said that what calculations are wrong. So we have to calculate. So after we have calculated, I think this senior physicist still disagree with me. And then the editor of Physical Review consulted the senior consultant again. The senior consultant said, publish the 2 papers, yeah. Let people decide it, yeah. And years after that, I have to admit that I have made the error. He was right. He was. That my calculation is, the result of my calculation is not 0.83, should be 0.85, something like that. Higher or larger than the harmonic hydrogen. And then one of my colleagues from Colombia, Andes University in Colombia, asked me to collaborate because he has another mechanism to increase the radius there, or to decrease the radius, the so-called relativistic effect or something like that. And we combine this result and my result, and we have precisely 0.80. We published it in Journal of Makara Journal of Science. This is the local journal in this university. So I invited you, if you have undergraduate research which you want to publish, yeah, please consider this Makara Journal of Science. Yeah. Then after that, I have to admit I have made an error and I have no longer mood to uh, to to continue the experiment until one of my graduate student asked a topic about research and I give him this topic. Yeah. Oh yeah, we also investigate the effects of this proton radius variation on the neutron star radius. So you vary the proton radius, you will also vary the radius of neutron star. Why? Neutron star contains of the neutron in principle, but there is also proton. So the effect of this proton size or proton radius variation is also sensitive to the neutron star radius. We have published it, yeah. Okay, it's not true. And then this is the latest progress, which I told you that I give this topic to my graduate students. Okay, let's start again with several compactors model. Let's model the compactor. We have the standard dipole compactor. You see that 0.71, yeah, we call standard. We can also write this because 0.84 squared is 0.71. This is called lambda. And we have general dipole compactors. This is the same like this. Just replace 0.71 with lambda squared. Yeah? Okay. There is also a model in the literature which is called double dipole. Why? Because this is dipole, this is dipole. This looks like this. Just replace lambda squared with Q1. Okay. This is A2. So we have two dipoles. So the compactor is called double dipole compactor. A0, 1 minus A0, just to normalize. If you put A0 equal to 1, then this term vanishes. If you put A0 equal 0, then so this is combination. Friedrich and Walter in Mainz in Germany has also another model. Friedrich is one of professor, experimental professor, yeah, in Mainz. Walter also experimental is there. They have the so-called, okay, we call it. They do not say this is our compact, but we call it Friedrich Walter compact. Contains two terms: the dipole, double dipole, plus the no structure or the smooth one. So no structure is this term. Involves exponential. And finally, the last one is Arrington. Arrington is a senior physicist I think in Seattle. He has this compactor. Of course, this can be expanded until infinities, but it stopped at tau to 3 and tau to third, and so this fifth power of fifth, yeah, power of 5. And this tau is equal to q squared divided by tau squared and equals to. So we have 1, 2, 3, 4, 5 different compactors, and we investigate this compact. This is the result, yeah, data very much. But we found that to represent this compactor using this representation, which I show you before, like this, yeah. Let me go back. Just electric compactor function of Q squared. We cannot find anything as something interesting. This is just like a dipole. But how about if we present it as a difference between the compactor and standard dipole? We can see the structure here. This is very interesting structure. Here you cannot see the structure. If you just plot it, it's a function of the square. The difference from the previous plot, here we use the logarithm plot, but still we cannot see. If we divided it by the standard dipole form factor, we have seen the structure, but the structure is very diffuse. We cannot see clearly. But we found that the difference between the form factors and the standard dipole form factor show a clear structure. It was found by Friedrich and Walter, I think, yeah, a long time ago, but they did not present the result using this representation, GE minus. So there is a topic, physical background, some physical process, physical dynamics, which produce this structure at Q squared approximately equal to 0.2 GeV. Now, if we zoom this structure, see that the structure really exists, and we compare the different models explaining this structure. Of course, the dipole cannot explain the structure because it has only one we call it deep or one structure. Using Friedrich Walter can be best explained the data because it has two structures here. And also using this is the repeated one, this is the original one. And using Arrington, we have also two structure, but seems to me doesn't fit very well. Yeah? But okay, we write in the paper, we need more data. Now this is the result. The open circles are our present result. We repeated the Friedrich Walter double dipole and also Arrington model. We also repeated the Pirat. This is Pirat is the new experiment in Jefferson Lab. They claim that they have very small radius, and we confirm that. We use dipole form factor, yeah, for the low data and also low data, and we found that most of our calculations are closer to the new monic hydrogen. So the conclusion is the problem of proton radius has not yet been solved now. Yeah, I think that's all. Yeah, because I think you are getting tired with this calculation and this result. So with this, I conclude this talk or this lecture. Now I would like to hear some of your questions, if any. Please. Do you have questions? Something to do with industry or with money and so on and so forth. This is only academic question, something like basic question. What is this universe made of? The building block of this universe, something like that. If you know the building block is a proton, how much the radius, how much the weight of the proton, the mass of the proton, something like that. That's fine. And then this is of course this is the business in the research. You have to know it precise, more precise, and more and more precise using the new technology. We don't know. Maybe in the next 10 years or next 100 years, the radius will change. Maybe back to the previous radius 0.88 Fermi or femtometer. We don't know. But this is really the basic question of the physics. Okay, nice question. Thank you. Is there any question? Yeah. Please. Yeah, we have plenty of time. I didn't know that this talk will finish so soon. Yeah. Because I prepared to write something on the board. Yeah, please. Just ask me a question if you have. Okay. Or question? Yeah, please. Oh, spiritual. No. This is well, this is a theoretical consideration. Yeah. For example, if you interact, for example, let me take a time in this direction. So you have two particles, of course, going up. The particle is going up because time moves in this direction. Now they interact. And then when they are interacting, what are they doing? This is belief that they exchange things. Maybe photon, maybe antiparticle. It depends on the interaction. If the interaction is electromagnetic interaction, they exchange photon. If the interaction is a strong interaction, now in the nuclear physics they said they exchange meson, which finally made the Yukawa win the Nobel Prize. Meson. But nowadays people move to higher and high energy. They said that they interact by exchanging gluon. Glue, you know glue, yeah? Article is gluon. Gravitation between our Earth and the Sun is mediating by the particle. So Sun and the Earth exchanging the particles called graviton. But unfortunately, this graviton is massless. And until now, people don't know how to detect the graviton. The problem is like that. Of course, this point of view or this consideration or this theory is different from the relativistic theory. In the relativistic case, the interaction is made by the what do you call this space-time curve. Space-time curve. But particle physicists said that the Earth and the Sun exchanging gravity. Yeah. Now, the exchange particle is virtual. Why? Because it is emitted and absorbed in a very short time. Very short time. Theoretically, experiment cannot measure it. Very. And if you calculate this is the so-called bound particle. Bound particle means this is bound. Bound particle. The bound particle is not the same like a free particle. As I told you before, in the case of free particle, the square of momentum or momentum is equal to the mass of the particle square. But in the case of bound particles, the square of the or momentum could be negative. So negative mass, and even the square of mass is negative, is a very funny thing. That means the mass should be imaginary. Yeah? Mass is imaginary. This is the virtual. This is so-called virtual. This is the theoretical point. Very good question. Yeah, please, if you have another question, just curious question is also good, yeah. Or a question beyond this topic is also maybe we can discuss if I could answer. Okay, would like to hear one more question from you. Oh, I have a question. How about the quantum mechanics course? Do you already have this course before? Which quantum mechanics? Advanced quantum mechanics? Not yet, yeah. Relativistic quantum mechanics? Not yet. Of course. After relativistic quantum mechanics, you can go to quantum field theory and quantum thermodynamics, and finally you will end up with the quantum computing. This is a very, very, very interesting topic, yeah. Why we need relativistic quantum mechanics? Because the particle in this scattering is relativistic, are relativistic, the particles. Yeah, I also forgot to say that in the beginning, we cannot see the proton because proton is hidden by the Heisenberg uncertainty relation. Why? Because we don't know where is the electron and where is the proton precisely. Yeah? Okay. Is there any student, some of you would like to make maybe bachelor dissertation, bachelor thesis in particle physics, physics? No? No. This is from the University of Malaya. I know the what's the chairman? What's his name? Do you know Professor? Yeah. Oh, I met him several times. Him. He was the chairman department physics. Huh? Department of Physics. Huh? Hassan, yeah? Yeah, Hassan, yeah. I met him. He's no longer retired. He was a nuclear physicist, nuclear particle physicist. Yeah? Theoretical? No? No, you don't know. You're gonna recall. Oh, we can search here, yeah. Let's see here. Um, let's say physics Malaya. yeah, the particle, yeah, maybe particle or nuclear. Here, maybe it's already retired. Up, people. Yes. Hasan Abu Karim, yeah. There is no, yeah, I think it's, yeah, I was also, I was asked also for, yeah, I think Hasan Abu Karim. Yeah, exactly. Okay, okay. Yeah, he's retired. Yeah. So, yeah, one or twice I was asked as examiner of the PhD thesis or something like that. Yeah, from for his student. I forgot. Yeah, twice I think. Particle physics. Then after that, I saw that maybe only material science are the bigger group there. Yeah, there is no longer particle physics. Do you have the course? But do you have a staff or? Oh, mhm. Taking part in his theories or experiment? Theory. Yeah, usually it's difficult to state experiment if you don't have experiment. He must collaborate with the collaboration outside to have accelerators. One of my former students collaborate with CERN, yeah, and he can survive because he's now still collaborating. Oh, one of my former students, Adi Sumowi Doctor, still 5 years, no longer fine, but he still only to the school. He is, yeah, he's experimentalist. You can see that number of paper may be huge, yeah, and also each index is citation is and this is the paper about the God particle, the Higgs particle, the finding of the particle. So if you want to stay in experiment, you have to collaborate experimentalists like this. Yeah. Cited by 20,000, 22,000 papers. Yeah, why? Because this is the God particle, yeah, the Higgs particle. So if you want to become experimental particle physics or nuclear physics, you have to collaborate in order to survive. Otherwise, you can stay like me, yeah, doing physics as hobby. Okay, more question? Yeah, please. How to calculate they know the spin and yeah, as long as I know, this is hypothetical particle. That means if you have quarks like this, charge is plus 2/3 yeah, then you have proton. So there is some calculation about the wave function, as I know, but for the quarks properties is hypothetical. This the properties came up in order to produce the proton properties. And of course, there are some consequence once you have quark like that. So this is what people are interested in, or people are searching the consequence of this hypothetical quark. So I don't think that there is a basic calculation from the first principle to produce this quark charge or quark spin. But because this is hypothetical, it means that if you have quark with spin 1/2, if you have this quark with charge a fraction of 1/3, then you will have protons which you observe in something like that to make it clear. Okay. Nowadays, I don't think people can have a calculation which produce, for example, the mass of the proton, the mass of the electron, precisely. Yeah? No, I don't. Frank will say that it is too difficult to produce, and he believes there is no theory of everything which can produce with one theory produce the mass of electron, the charge electron, mass of proton. Still also long mystery. Yeah? Good. Is there any question? I would like to ask you, yeah, what kind of physics are you, let's say, are you pursuing after this? I mean, for a bachelor thesis or bachelor research, material science. Who would like to? No material science. Material physics. No, after this, yeah. Now, of course, you are studying physics, yeah. In our department, we have so-called specialization. Previously, we have very different specialization. For example, my group is theoretical nuclear, particle, and astrophysics. And there is instrumentation physics. There is also material science or material physics. And there is also medical physics. So people, undergraduate students, can also go to this group for the bachelor thesis. I don't know in your case. Already. Only a few of you. Not all, not the whole, not all. Okay. And so I think I have done this lecture. I would like to finish. If you still have question, please raise your hand now. Otherwise, I thank you very much for your participation in this lecture. Yeah, thank you very much. And I wish you have a successful summer school here. Yeah, thank you very much. Assalamualaikum.